Hi, my name is Lucas Lopez-Jensen, and today I'll be helping you put trigonometry back together.
So, after the last episode on graphs, you should all be more comfortable with the idea of trig ratios as functions. You know that there's always an output or undefined point for every input that they can have, and that they act pretty predictably. With this information, we can start using trig functions in more conventional math. In this episode, we'll be using sine, cosine, and tangent, and sometimes cosecant, secant, and cotangent to logically solve math problems. If you're like me, this episode is going to be lots of fun to puzzle through and figure out. If you're like most people, well, maybe at least you'll learn something. Anyway, there are certain ways that certain trig functions interact with each other that can always be predicted, and we can use these interactions or identities to do math. Let's start with the most important one. Some people call it the fundamental identity. It states that sine squared of x plus cosine squared of x equals 1. While this may seem random, it's actually pretty solidly based on the Pythagorean theorem. Let's turn to the unit circle. Recall that in the right triangles made by all of our special angles, cosine is represented by an x value and sine is represented by a y value. So on this triangle, we have two leg lengths. One is cosine and the other is sine. The third side, the hypotenuse, is 1 because that's the radius of the unit circle. Now, remember that the Pythagorean theorem states a squared plus b squared equals c squared. In the case of this triangle, or any triangle on the unit circle, a and b could be sine or cosine. It doesn't really matter which. So, plugging in the values of all of our legs, we get that sine squared of x plus cosine squared of x equals 1. And this works with any values of sine and cosine, as long as you use the same x value for both functions. An easy example of this is the value of 0. Sine of 0 is 0, so sine squared of 0 is also 0. Cosine of 0 is 1, so cosine squared of 0 is also 1. In this case, it's pretty clear that sine squared of x plus cosine squared of x equals 1. If you're curious, go ahead and try plugging in pi over 6 for x, using the unit circle values to solve for sine and cosine. You should get an answer of 1 for sine squared of x plus cosine squared of x, but to save time, I won't do all the math in front of you. Sine squared of x plus cosine squared of x equals 1 is only one of 3 Pythagorean identities which are based on the Pythagorean theorem. It's definitely the most important one, but there are 2 more I should show you. The next Pythagorean identity is 1 plus cotangent squared of x equals cosecant squared of x. And whoa, this identity looks weird. There's a bunch of squared inverse functions in it, and it's kind of hard to make sense of. To remedy this, let's put it in terms of sine and cosine. Simplifying the inverse functions, we get 1 plus cosine squared of x over sine squared of x equals 1 over sine squared of x. Because cotangent is cosine over sine, and if it's squared, all of its inputs must be 2. The same goes for cosecant, which is just 1 over sine. Now, to get matching denominators to add the fractions, let's substitute sine squared of x over sine squared of x in for 1. Now we have sine squared of x over sine squared of x plus cosine squared of x over sine squared of x equals 1 over sine squared of x. With that, we can start doing real math. Our first 2 values have a common denominator of sine squared of x, so we can combine them as like terms to make sine squared of x plus cosine squared of x divided by sine squared of x is equal to 1 over sine squared of x. And recalling our Pythagorean identity, we know that sine squared of x plus cosine squared of x equals 1, so our function comes down to 1 over sine squared of x equals 1 over sine squared of x. So we just proved the second Pythagorean identity. And that process we went through of rewriting the equation in other terms and using past identities to further simplify it is the process of doing trig proofs. With all this information in mind, let's tackle the third one. The last Pythagorean identity is tangent squared of x plus 1 equals secant squared of x. But before I get into it, I want you all to try it. Go ahead and pause this screen and unpause when you think you've proven that both sides of this equation are equal. Ready? Let's go. Again, to simplify this one, let's put it in terms of functions we have rules for, sine and cosine. We should get that sine squared of x over cosine squared of x plus 1 equals 1 over cosine squared of x.
Does that check out?
Yep.
Yeah.
Is that real math? That's real math.
Okay.
Now, so that we can get a common denominator to add the first 2 values together, let's rewrite 1 as cosine squared of x over cosine squared of x. This gives us sine squared of x over cosine squared of x plus cosine squared of x over cosine squared of x equals 1 over cosine squared of x. Combining like terms, we get sine squared of x plus cosine squared of x over cosine squared of x equals 1 over cosine squared of x. And plugging in the fundamental identity, we get 1 over cosine squared of x equals 1 over cosine squared of x, or secant squared of x equals secant squared of x. And that's all the Pythagorean identities explained. There are many, many more trigonometric identities more complicated than these, but the Pythagorean identities should give you a good introduction to the concept. Before the video ends, we'll see if you can solve a trig proof involving these identities, and I'll introduce one more concept afterward. Using what you know about the Pythagorean identities, see if you can prove the following. 1 minus cosine squared of x over secant squared of x minus 1 is equal to cosine squared of x. Go ahead and pause, try to solve it, and play the video when you're done. So the first thing to notice about this problem is that it includes 1 minus cosine squared of x. We know that sine squared of x plus cosine squared of x equals 1, so 1 minus cosine squared of x equals sine squared of x. Let's plug that in to get sine squared of x over secant squared of x minus 1 is equal to cosine squared of x. Next, I notice that the problem includes secant squared of x minus 1. We know that tangent squared of x plus 1 equals secant squared of x, so secant squared of x minus 1 equals tangent squared of x. Let's put that in too to get sine squared of x over tangent squared of x equals cosine squared of x. Now recall that tangent squared of x equals sine squared of x over cosine squared of x. If that doesn't make sense, remember that tangent equals sine over cosine, and if you square a numerator and a denominator, you square the quotient too. So let's add that to the equation to get sine squared of x over sine squared of x over cosine squared of x equals cosine squared of x. Remember that dividing by a fraction is the same as multiplying by its reciprocal, so we get sine squared of x over 1 times cosine squared of x over sine squared of x equals cosine squared of x. This simplifies to sine squared of x times cosine squared of x divided by sine squared of x equals cosine squared of x. And now we can factor out the sine squared of x to finally get that cosine squared of x equals cosine squared of x. Hopefully that made sense, and if it didn't, don't worry, this is going to be the only trig proof I'll show you in this series. Before I end the video, there's just one more thing I want to talk about. All of the 6 basic trig functions can be considered even or odd. When these words are referring to functions instead of numbers, it's actually a comment on the shape of their graphs. Even functions are symmetrical about the y-axis, so they'd look the same if you flip them over it. Odd functions, on the other hand, are rotationally symmetrical about the origin. Essentially, that means you could flip the function around the center of the graph and have it look the same. So, by definition, in an even function f of x equals f of negative x. Opposite inputs, like pi and negative pi, would give the same output. In an odd function g of negative x equals negative g of x. Putting in an opposite input would basically do the same thing as making the whole function negative, flipping it about the origin. As you may be able to tell, cosine is an even function and sine is an odd function. So as you can see here, cosine is an even function because it's symmetrical about the y-axis. And as you can see here, sine is an odd function because it's symmetrical about the origin. So if cosine is even and sine is odd, cosine of x equals cosine of negative x, and sine of negative x equals negative sine of x. If we add tangent into the mix, we'll see that like sine, it's symmetrical about the origin. So tangent is an odd function, and tangent of negative x equals negative tangent of x. I won't quiz you on these, but it's good to know how each function reacts when reflected on a key point about the graph, and these identities should generally help you understand the function's behavior better. Next time, we'll be venturing into the exciting new world of calculus and taking the derivatives of trig functions. If that sounds totally alien and weird to you, I'll definitely explain it further in the next video. Until then, I've been Lucas, and I hope that now trigonometry is a little less broken.